Hey, I've been reading about the evolution of computers, and it's fascinating how much they have changed over the years. Do you know much about the different generations of computers?
Yeah, I do. It's really interesting how the technology has evolved. Each generation of computers represents a significant leap in technology. Let's start from the beginning, the first generation.
Sure, the first generation. I know it began around 1940 and lasted until about 1956. The computers back then were massive, right?
Exactly. The first generation computers were developed using vacuum tubes, which are these glass tubes that control electrical signals. They were huge, often taking up entire rooms, and they generated a lot of heat, which made them quite inefficient.
Right, I remember reading about some of the examples like the IBM 650 and IBM 701. These computers were primarily used for basic arithmetic calculations and military purposes, weren't they?
That's right. They were mainly used for scientific calculations, and programming them was quite a challenge since it was all done using machine language, the most basic level of programming.
And then came the second generation of computers, around 1956 to 1963. This was when transistors replaced vacuum tubes, if I'm not mistaken.
Exactly. The use of transistors marked a significant shift. Transistors were much smaller than vacuum tubes and didn't generate as much heat, making computers more reliable and less expensive. This led to smaller, faster, and more energy-efficient computers.
It's amazing how quickly technology advanced. The IBM 1400 series and the IBM 7090 and 7094 computers are examples of this generation, right?
Yes, those are good examples. With transistors, computers became more widely used in business, universities, and government organizations. Also, programming languages like COBOL and Fortran started becoming popular during this era, making it easier to write programs for these machines.
Then came the third generation, from 1963 to 1971. This was the era of integrated circuits, or ICs. I think this is when computers started to become even smaller and more powerful.
You've got it. Integrated circuits allow dozens of transistors to be packed into a single silicon chip, drastically reducing the size of computers and increasing their efficiency and speed. This generation also saw the rise of operating systems, which allowed multiple programs to run at the same time.
The IBM 360 and IBM 370 were some of the notable computers of this generation, weren't they?
Yes, exactly. The IBM 360, for instance, was quite revolutionary because it could be used for both scientific and business applications, making it a very versatile machine. The IBM 370 further improved on this with better performance and reliability.
After that, we enter the fourth generation, which is from 1972 to about 2010. This is when microprocessors and very large-scale integration (VLC) technology came into play, right?
Correct. The development of microprocessors was a game changer. A microprocessor is essentially the computer's central processing unit (CPU) on a single chip, which made computers even smaller, more powerful, and more affordable. This led to the creation of personal computers, which revolutionized how we interact with technology.
The IBM PC, Apple II, Apple Macintosh, and Altair 8800 are all examples of fourth-generation computers, aren't they?
Yes, those were some of the iconic computers of the fourth generation. This period also saw the rise of graphical user interfaces, GUIs, which made computers much easier to use. It was during this time that computers started becoming a household item.
And now we're in the fifth generation, which started around 2010. This generation isn't just about hardware, right? It also includes software advancements.
Exactly. The fifth generation is characterized by the incorporation of advanced technologies like artificial intelligence, AI, quantum computing, and nanotechnology. It's not just about making computers faster or smaller. It's about making them smarter and more capable of performing complex tasks.
So, computers today can perform multiple tasks simultaneously, thanks to parallel processing and AI, right?
Yes, That's one of the big advancements. AI allows computers to learn from data and improve over time, which is why we see it being used in everything from voice assistants like Siri and to more complex applications like autonomous vehicles and personalized medicine.
Quantum computing is another big one, isn't it? I read that it has the potential to solve problems that are currently impossible for classical computers to solve.
Absolutely. Quantum computing leverages the principles of quantum mechanics to process information in ways that classical computers can't. It's still in its early stages, but it has the potential to revolutionize fields like cryptography, material science, and complex systems modeling.
And what about nanotechnology? How does that fit into the fifth generation?
Nanotechnology involves manipulating matter on an atomic or molecular scale, which can lead to the creation of incredibly small and efficient devices. In computing, it could mean even more powerful processors and memory devices that consume less power and generate less heat.
It's incredible how much has changed from the vacuum tubes of the 1940s to the advanced AI and quantum computers of today. The evolution of computer technology is truly remarkable.
It really is. And the best part is, we're just scratching the surface of what's possible. The future of computing is going to be even more exciting.
I can't wait to see what comes next. Thanks for breaking this all down. It's been really enlightening.
Anytime. It's always fun to talk about technology. Let's keep an eye on the latest developments together.
Hey, I've been digging into how computers actually work, and I came across some information about the CPU and its speed. It's pretty amazing how central the CPU is to everything a computer does.
Absolutely. The CPU, or Central Processing Unit, is often called the brain of the computer because it's responsible for executing instructions and performing calculations. It's essentially the core of any computer system.
That makes sense. So, the CPU is just like a processor, right? I've heard those terms used interchangeably.
Yes, that's correct. The CPU is also known as a processor. It's an electronic microchip or microprocessor that performs processing based on the instructions given to the data by the user. This means every time you run a program or perform a task on your computer, the CPU is working hard to make it happen.
I see. And what about the parts of the CPU? I heard there are three main parts: ALU, CU, and MU. Can you explain what each of these does?
Sure, let's break it down. The CPU consists of three main parts. 1. ALU, arithmetic and logical unit. This is a fundamental component that performs arithmetic operations, like addition and subtraction, as well as logical operations, like comparing numbers. Basically, whenever you perform a calculation or any kind of logical decision-making in a program, the ALU is doing the heavy lifting. 2. CU, control unit. The control unit is like the traffic cop of the CPU. It controls what happens inside the computer by directing the operation of the processor. It manages and coordinates all the activities within the computer, ensuring that instructions are executed in the correct sequence. 3. MU, memory unit. The memory unit, often referred to as the main memory or RAM, random access memory, is the component that stores data, programs, and information that the CPU needs to access quickly. It's like the short-term memory of your computer.
That's really cool. So, these parts work together to perform all the processing tasks in the computer. What about the components within the CPU, like registers, cache, and buses? How do they fit into the picture?
Great question. These components are crucial for the CPU's operation. Registers are small, high-speed storage locations within the CPU. They are used to hold temporary data and instructions that the CPU is currently processing. Because they are directly connected to the processor, they can be accessed much more quickly than any other part of the computer. Cache memory is even faster than RAM and is used to store frequently accessed data and instructions to speed up processing. When the CPU needs some data, it first checks the cache. If the data is there, it can save time instead of going all the way to the slower main memory. Buses are communication pathways that connect various components of a computer system. There are three main types of buses: O address bus, This is a unidirectional bus that carries the addresses of data from the CPU to other components. It tells the computer where to find or store data. O data bus. This is a bidirectional bus that carries the actual data between the CPU, memory, and peripherals. O control bus. This is also bidirectional and carries control signals within the CPU and to other parts of the computer. It's responsible for coordinating the actions of all the components.
That makes a lot of sense now. The CPU really is the central hub of activity in a computer. What about the CPU clock? I've heard the term clock speed mentioned a lot when people talk about CPU performance. What exactly is that?
The CPU clock is like the heartbeat of your computer. It's a small electronic circuit that generates a timing signal, which synchronizes the operations of all the components. The clock speed, measured in hertz, indicates how many cycles per second the CPU can execute. For example, a CPU with a clock speed of 3 GHz can execute 3 billion cycles per second. The higher the clock speed, the more instructions the CPU can process in a given amount of time, which generally means better performance.
Wow, so the clock speed is really crucial for determining how fast a CPU can process tasks. I guess that's why people are always looking for CPUs with higher clock speeds when they want a faster computer.
Exactly. However, it's important to note that clock speed isn't the only factor that affects a CPU's performance. Other factors like the number of cores, cache size, and architecture also play significant roles. But you're right, clock speed is a key indicator of how fast a CPU can execute instructions.
Interesting. And what about input and output devices? I know they're essential for interacting with a computer, but how do they fit into the whole CPU and processing picture?
Input and output devices are crucial for communication between the user and the computer. Input devices. These are devices that allow users to send signals to the computer to perform tasks. The CPU receives these signals and processes them accordingly. Examples of input devices include a keyboard, the most common input device, used for typing text and commands. Pointing devices. These include mice, trackballs, touchpads, and light pens. They allow the user to interact with the computer's graphical interface. Scanners, used to digitize physical documents into digital format. Webcams and microphones. Webcams capture video, while microphones capture audio, both of which are processed by the CPU. Output devices. These are devices that display or output the results of the computer's processing. The CPU sends data to these devices to present the final output to the user. Examples of output devices include monitors, also known as visual display units, VDUs. They display images and text by arranging pixels in patterns. Printers produce hard copies of digital documents. Projectors display visuals on a larger screen, often used for presentations.
So input devices send data to the CPU, which processes it, and then output devices display or produce the results. That's pretty straightforward. What about devices that are both input and output?
Good point. There are indeed devices that function as both input and output. These are often called input/output devices or input-output devices. Examples include touchscreen monitors. These act as both an input device when you touch the screen and an output device, displaying images and text. External drives. These can receive data from the computer input and also provide data back to the computer output. Network cards. These receive data from the network input and send data to the network output.
It's amazing how all these components work together seamlessly. The CPU really does play a central role in everything, from processing data to coordinating with input and output devices.
Absolutely. The CPU is integral to the functionality of a computer. Understanding how it works helps us appreciate the complexity and efficiency of modern computers.
I was just looking at this diagram about different types of computer memory, and it got me thinking about how crucial memory is to a computer's functionality. Can we go over the different types of memory and storage?
Absolutely. Memory in a computer is a lot like the human brain. It's used to store data, instructions, and information. It's essential for a computer's operation because it holds the data that the CPU processes. We can broadly categorize computer memory into three types: primary memory, secondary memory, and cache memory.
That sounds like a good place to start. So, what exactly is primary memory?
Primary memory, also known as main memory, is the memory that the computer uses to store data and programs that are in active use. It's directly accessible by the CPU and is much faster than secondary storage. Primary memory includes two types: RAM, random access memory, and ROM, read-only memory. RAM, random access memory, this is a type of volatile memory, which means it only stores data while the computer is powered on. When you turn off your computer, all the data in RAM is lost. It temporarily stores programs and data that the processor needs while performing tasks. ROM, read-only memory, unlike RAM, ROM is non-volatile. This means that the data stored in ROM remains even when the computer is turned off. It's used to store important instructions that are required to start up the computer, like the BIOS. As its name suggests, ROM is read-only, so the data stored here can't be easily modified.
I see. So RAM is where the computer does its thinking, storing everything it's currently working on, and ROM is more like the long-term memory, storing essential startup instructions. What about secondary memory? How does that fit into the picture?
Secondary memory or storage is a non-volatile type of memory, which means it retains data even when the computer is turned off. It's used to store large amounts of data permanently. Unlike primary memory, secondary memory is slower, but it's much more cost-effective and can store much more data. A computer system can technically operate without secondary memory, but it wouldn't be practical since it wouldn't have a place to store data long-term.
That makes sense. What are some examples of secondary memory?
There are several types of secondary memory. Magnetic tapes. These are long, narrow strips of plastic film coated with a magnetic material. They were one of the earliest forms of secondary storage, mainly used for archival purposes because they can store large amounts of data, but they are quite slow. Hard disks or magnetic disks. These are the traditional storage devices used in computers. They consist of flat, circular plates coated with a magnetic material. Hard disks can store large amounts of data and are relatively fast, making them ideal for everyday use. Solid-state drives, SSDs, these are much faster than hard disks because they use non-volatile flash memory. SSDs have no moving parts, making them more durable and quicker to access data. Optical disks, these include CDs, DVDs, and Blu-ray discs. They use lasers to read and write data and are relatively inexpensive with a long lifespan. They come in different capacities, like CDs holding around 600 megabytes, DVDs about 4.7 gigabytes, and Blu-ray discs up to 50 gigabytes. Optical discs can be further categorized into ROM, read-only, and R/RW, rewritable.
That's a pretty diverse set of storage options. Each seems to have its strengths depending on what you need. And what about cache memory? How does it differ from the other types?
Cache memory is a type of high-speed semiconductor memory that can greatly speed up the CPU's processing by storing frequently accessed data and instructions. It acts as a buffer between the CPU and the main memory, helping to reduce the time it takes for the CPU to access data from the slower main memory.
So, cache memory is kind of like a middleman that speeds things up by keeping the most used data close at hand. What about registers? I saw them mentioned in the diagram too.
Good observation. Registers are small amounts of high-speed memory located directly within the CPU. They hold temporary data and instructions that the CPU is currently processing. Because they are the fastest type of memory, the CPU accesses them first when performing calculations. They play a critical role in the overall speed and efficiency of the CPU.
That's fascinating. And what's the significance of the memory hierarchy I see in the diagram?
The memory hierarchy in the diagram illustrates the relationship between access time and capacity across different types of memory. As you go higher up the pyramid, you find faster memory types like registers and cache, which have lower capacity. As you move down, you find slower memory types like magnetic disks and tapes, which have much larger capacities. The hierarchy shows how each type of memory balances speed and storage capacity to optimize a computer's performance and cost.
That makes perfect sense. The faster, smaller memories are closer to the CPU to speed up processing, while the slower, larger memories handle long-term storage. Thanks for breaking it all down. This really helps me understand how computers manage and store data.
Anytime. Understanding memory types and storage is fundamental to understanding how computers work. It's amazing how these different components work together seamlessly to handle all kinds of data efficiently.
I've been learning about different types of software, and it's pretty amazing how diverse they are. Can we discuss the various types of software, like system software, application software, and utility software?
Absolutely. Software is essentially a set of instructions or commands that tell a computer what to do. There are several types of software, each serving a unique purpose in a computer system. Let's start with system software.
Sure. What exactly is system software?
System software is software that directly operates the computer hardware and provides the basic functionalities required for other software to operate smoothly. It serves as a bridge between the hardware and the user. There are three main types of system software. 1. Operating system, OS. This is the main program of a computer system. It manages all the computer resources, such as memory, CPU, printers, and hard disks, and provides an interface for the user to interact with the computer. Common examples of operating systems are Linux, Apple macOS, and Microsoft Windows. 2. Compiler/interpreter. These are programs that convert code written in high-level programming languages like Java, C, C++, and Python into machine code that the computer can understand and execute. A compiler translates the entire code at once, while an interpreter translates it line by line. 3. Device driver. A device driver is software that controls a specific hardware device attached to the computer, such as a printer, mouse, or modem. It acts as a translator between the hardware and the operating system, allowing the device to perform its functions properly.
That makes a lot of sense. So, the operating system is like the foundation of a computer's software environment, while compilers, interpreters, and device drivers help translate and control other software and hardware.
Exactly. Now, let's talk about application software.
Application software is designed to perform specific tasks for end users, right?
Yes, that's correct. Application software is created to help users perform particular tasks. This can range from simple tasks like word processing or creating spreadsheets to more complex tasks like graphic design or video editing. Unlike system software, which runs in the background, application software is what users interact with directly.
So, examples of application software would be things like Microsoft Word, Excel, and Adobe Photoshop.
Exactly. These are all types of application software designed to fulfill specific user requirements. Now, let's move on to utility software.
Utility software sounds like it helps manage and optimize the computer system. Is that right?
Yes, that's spot on. Utility software is designed to analyze, configure, optimize, or maintain a computer system. It includes programs that help manage system resources, like antivirus software that protects against malware, or disk cleanup tools that free up space on your hard drive.
I see. So, utility software works to keep everything running smoothly and efficiently. Speaking of antivirus software, what's the role of security software in a computer system?
Security software is crucial for protecting your computer from threats. It includes tools like antivirus software. This software is designed to detect, prevent, and remove viruses and other malicious software from your computer. It scans your system for known viruses and can quarantine or delete them to prevent damage. Anti-spyware. This software detects and removes spyware, which is a type of malware that collects information from your computer without your consent. Anti-spyware tools help protect your privacy and keep your data secure. Firewall. A firewall is either a hardware or software-based security system that monitors and controls incoming and outgoing network traffic based on predetermined security rules. It acts as a barrier between your internal network and external networks, such as the internet, to block malicious traffic and prevent unauthorized access.
That's really important. It's great to know that these tools are there to protect our systems from various threats. I've also heard terms like proprietary software, shareware, open source software, and freeware. What do those mean?
These terms refer to different types of software based on how they are distributed and used. Proprietary software. This software is privately owned and distributed under specific licensing terms that restrict the user's ability to modify, distribute, or access the source code. It's controlled by the company or individual who created it. Examples include Microsoft Office and Adobe Photoshop. Shareware. Shareware is commercial software that is distributed for free, often as a trial version. After a certain period, the user is encouraged or required to pay for continued use or access to additional features. Examples include WinRAR and some antivirus programs. Open source software. This software is distributed with its source code, allowing users to use, modify, and distribute it freely. It promotes collaboration and sharing within the community. Examples include Linux and Apache HTTP server. Freeware. Freeware is software that is available at no cost. Users can download and use it without paying, but they usually don't have access to the source code. Examples include Google Chrome and Skype.
That's a great breakdown. It's interesting how each type of software has different rules and usage rights. What about malware? I've heard that term a lot, especially in the context of cybersecurity.
Malware stands for malicious software, which is designed to cause harm to computer systems, networks, or users. There are several types of malware, each with its own way of damaging or exploiting systems. Viruses, malicious code attached to another executable file. When the infected file is shared, the virus spreads to new systems. Worms, these replicate themselves on a system, spreading to other files and seeking out pathways to other computers, often through networks. Trojan horses, these appear to be legitimate programs, but carry out malicious activities in the background, like stealing data or allowing unauthorized access. Spyware, its main purpose is to steal private information from a system and send it to a third party, often without the user's knowledge. Keyloggers, these record everything a user types to capture sensitive information, like passwords, and send it to the hacker.
Malware sounds really dangerous. It's good to have security measures in place, like firewalls and antivirus software, to protect against these threats.
Absolutely. It's crucial to have robust security software and practices to protect your computer and personal data.
I came across this chart on different data units and speeds, and it got me thinking about how data is measured and managed in computers. Could we go over some of the basics?
Of course. Data units and memory units are fundamental concepts in computing. They help us understand how much data we can store and how fast data can be processed or transferred. Let's start with the basic unit of data, which is the bit.
A bit, right? I've read that a bit can be either a 0 or a 1. How does that fit into the bigger picture?
Exactly. A bit is the most basic unit of data in computing and represents a binary state, either 0 off or 1 on. Bits are the building blocks for all other data units. When you group bits together, you get more meaningful units of data. Nibble, a group of 4 bits. It's not commonly referenced, but it's good to know for understanding the structure of data. Byte, a group of 8 bits. The byte is the standard unit for measuring data size in computers. It's used to represent a single character, such as a letter or a number.
So, a byte can store enough data to represent one character, like a letter in a Word document. What comes after a byte?
Yes, that's right. Beyond bytes, data is measured in larger units, each being a multiple of bytes. Kilobyte, kilobits. 1 kilobits is equal to 1024 bytes. It's often used to measure small files, like text documents. Megabyte, megabytes. 1 megabyte is equal to 1024 kilobits. This is a common unit for measuring file sizes like images or songs. Gigabyte, gigabytes. 1 gigabyte is equal to 1024 megabytes. It's used to measure larger files like videos or the storage capacity of a USB drive. Terabyte, terabytes. 1 terabyte is equal to 1024 gigabytes. This unit measures very large storage capacities, such as those found in external hard drives. Petabyte, PB, exabyte, EB, zettabyte, ZB, yottabyte, EB, bruntobyte, and gigabyte. These are progressively larger units used for measuring massive amounts of data, like the storage capacity of large data centers or the amount of data transferred over the internet globally.
Wow, that's a lot of data. I noticed that each unit is 1024 times the previous one instead of 1000. Why is that?
Great observation. That's because computers operate using binary, base 2, rather than decimal, base 10. So, each step up in data size is actually a power of 2. For example, 1024 bytes is 2 circumflex 10, which is why a kilobyte is 1024 bytes instead of 1000.
That makes sense. Computers really are all about those 0 seconds and 1 second. What about ASCII? I've heard it's related to how computers handle text.
ASCII, or the American Standard Code for Information Interchange, is a character encoding standard used for electronic communication. It uses 8 bits, or 1 byte, to represent each character. ASCII includes letters, numbers, punctuation marks, and some control characters, with a total of 256 possible characters.
So, ASCII is how computers convert text into binary code, using a byte for each character. That's pretty cool. What about data transmission and emails? I know emails involve different protocols.
Absolutely. When it comes to email, several protocols govern how emails are sent and received over the internet. SMTP, Simple Mail Transfer Protocol. This is the protocol used for sending emails. When you hit send, your email client uses SMTP to push the email out to the recipient's email server. POP, Post Office Protocol. This protocol is used to retrieve emails from the server to a single client. It downloads the emails to your device and typically deletes them from the server, allowing offline access. IMAP, Internet Message Access Protocol. Unlike POP, IMAP allows you to access your emails directly on the server without downloading them. This is useful for managing your emails across multiple devices since the changes you make, like reading or deleting an email, are reflected everywhere. MIME, Multi-Purpose Internet Mail Extensions. This protocol extends the format of email to support text and character sets other than ASCII, as well as attachments like images, videos, and other media types.
So SMTP is for sending, POP is for downloading emails to one device, and IMAP is for managing emails on multiple devices. And MIME allows for attachments in different text formats. That's a lot of coordination.
Exactly. And there are a few more terms and features of email clients that are useful to know. Inbox. This is where received emails are stored. It's the first thing you see when you open your email client. Outbox. This is where emails are temporarily stored before they are sent. If an email can't be sent right away, it stays in the outbox until it can be delivered. Spam folder. This folder is used to store unwanted emails that have been flagged as spam by your email service provider. Address book. This is where you store email addresses for easy access when sending emails. Email attachment. This is a file sent along with an email message. Attachments can include documents, images, videos, etc. CC, carbon copy, and BCC, blind carbon copy. CC is used to send a copy of the email to additional recipients, and BCC sends a copy without the other recipients seeing who else received it.
I've been trying to wrap my head around how the internet and websites work. It's such a vast topic, and I'd love it if you could explain some of the basics to me.
Absolutely. The internet is indeed a vast and fascinating topic. Let's start with the basics. The internet is essentially a massive network that connects millions of computers all over the world. Through the internet, people can share information and communicate with each other from anywhere with an internet connection.
That's pretty amazing. So, when we talk about accessing websites and web pages, how does that work exactly?
Great question. To understand that, we need to talk about web servers and web clients. Web server. A web server is a computer system that stores, processes, and delivers web pages to users over the internet. When you type a URL into your web browser, your request goes to the web server that hosts the website, and the server responds by sending the requested web page back to your browser. Web client, on the other hand, a web client is typically a web browser or a web application that connects to a web server over HTTP Hypertext Transfer Protocol. The web client displays the web pages received from the server and allows users to interact with them. For example, when you use browsers like Chrome, Firefox, or Safari, you're using a web client to access information on the internet.
That makes sense. So, the web server is like the library, and the web client is like the librarian helping you find the right book. What about the World Wide Web or WWW? Is it the same as the internet?
Not exactly. The World Wide Web, WWW, is a system of interlinked hypertext documents and multimedia content that is accessed via the internet. It's a collection of public websites and web pages that are connected through hyperlinks. While the internet is the infrastructure, the web is a service that runs on the internet, allowing users to access web pages and information.
Got it. So, the internet is the network, and the web is just one of the services we use over that network. What exactly is a website then?
A website is a collection of related web pages that are linked together and identified by a common domain name. All the web pages on a website are typically stored on the same web server. Websites are what we usually interact with when we're browsing the web.